Hello, welcome back to AE 3530, System Dynamics and Vibration. In this video, we're going to go through section 2.2 of our notes, which focuses on damped oscillations. We're going to consider the following viscously damped harmonic oscillator that includes both a spring and a damper coefficient K and C respectively. The equation of motion for this system is going to be mx double dot plus cx dot plus kx, and there's no forcing applied, so that will be equal to 0. We're going to divide by m, and we're going to rewrite equation 14 as x double dot plus 2 zeta omega n times x dot plus omega n squared x, and that is equal to 0 still, where here zeta is the damping ratio, and it is equal to C divided by 2m omega n, also equal to C divided by 2 square root of k times m, and of course C over m must be equal to 2 zeta times omega n. Like I said, zeta is known as the damping ratio, and C here is the damping coefficient, and it's very important to keep these separate and not confuse the terminology. Zeta is the damping ratio, and C is the damping coefficient. We're going to proceed by using the ansatz x of t equals a e to the lambda t, and then we're going to substitute that into equation 15, and then use that to find the solution to the equation of motion. So we're going to substitute that in, and we're going to end up with the quantity lambda squared plus 2 zeta omega n lambda plus omega n squared, all of that times a e to the lambda t equal to 0. Again, we find that a equals 0 is a possible solution, but this is a trivial solution. And e to the lambda t cannot be 0 for all time. And as a result, we will then consider only the solutions where lambda squared plus 2 zeta omega n lambda plus omega n squared is equal to 0. This is just a quadratic equation in lambda. We can use the quadratic formula to then find our two solutions for lambda. We'll get lambda 1 and 2 are equal to minus zeta omega n plus or minus omega n times the square root of zeta squared minus 1. So those are our two solutions for lambda here. So the behavior of the oscillator is going to change depending on the value of zeta. Specifically, we're going to be looking at what happens to this square root term that I'm circling right now. That term is going to change from being either imaginary to being real depending on the value of zeta. So first, if zeta is greater than 0 but less than 1, zeta cannot, if zeta is 0, then you get an undamped response, and we dealt with that in the previous section, so we're not going to consider that here. If zeta is less than 1 but greater than 0, we get what is known as an underdamped case. This case will lead to periodic oscillations that decay in amplitude. Case 2 is when zeta is equal to 1, and this is considered to be critically damped. Case 3 is when zeta is greater than 1, and this is considered overdamped. And both of these cases give rise to an aperiodic motion, meaning that there are no periodic oscillations. It's an aperiodic motion. Okay, we're going to go through each of these cases individually, starting with case 1, which we'll say is the underdamped case. This again is the only case that leads to oscillatory motion. And when zeta is greater than 0 but less than 1, we'll find that our solution lambda 1 and 2 will be equal to b minus zeta omega n plus or minus j omega n times the square root of 1 minus zeta squared. And here what we've done is we've pulled out an imaginary constant and we've switched the order inside that square root. And then we'll define what we call the damped natural frequency, which is omega sub d, and this is equal to omega n times the square root of 1 minus zeta squared. And that is the damped natural frequency. Note that the damped natural frequency is always going to be smaller than the natural frequency. So then we can write here that lambda 1, 2 will be equal to minus zeta omega n plus or minus j times omega d. Okay, we can then write the displacement of the oscillator, and we're going to bring in our initial conditions, and we're going to skip all of the algebra and identities. We're going to end up writing that the displacement of the oscillator is equal to, so x of t is equal to e to the minus zeta omega nt times the quantity x0 times the cosine of omega dt. So here we have the damped natural frequency inside the cosine term plus the fraction v0 plus zeta omega n times x0, all of that divided by omega d and multiplied by the sine of omega dt. And just like previous case, we can combine these two trig functions together, and then we can write that x of t is equal to e to the minus zeta omega n t times, in fact, we're going to move this over, and I'm going to redo that zeta. We're going to put a big C here, is times e to the minus zeta omega t times cosine of omega dt minus the phase angle phi, where c, big C, is equal to the square root of x0 squared plus that big fraction v0 plus zeta omega n x0, all of that divided by omega d, that big fraction squared, and the square root applied to all of that. And phi here, the phase angle, is the inverse tangent of zeta omega n x0 plus v0 over omega d times x0. Okay, before we go on to case 2, I've gone ahead and I've provided a plot here for different example responses. And what you can see here is that as we increase the damping ratio, the response will decay at a faster rate. It will decay faster and faster if zeta is increasing. We can also see in the dashed line there is an envelope there. This is the amplitude of the signal, and it is changing or decreasing over time due to the damping in the system. So that damper is constantly extracting and removing energy from the system, and as a result, this is then decreasing the amplitude of the displacement over time. Again, case 1 is underdamped, and this is the only case where we get periodic oscillations. We're now going to go on to case 2 here, which focuses on critically damped. This is when zeta is equal to 1, and in this case what we're going to find is that if we go back up, let me go up here, where were we? If we come back, and I'm going to copy this equation for lambda 1 and lambda 2. I'm just going to bring it down here for us to see. When zeta is equal to 1, we're going to get 0 under that square root, and then we're going to lose that. We're going to end up losing that that natural frequency. I'm sorry, we're going to end up losing that second term right here. And what we'll find is that lambda 1 must be equal to lambda 2, which must be equal to omega n, minus omega n, because zeta is 1. Okay, in this case, we end up with repeated roots, and as a result, the displacement of the oscillator, and we're not going to show this, but you can go through and show this. The displacement of the oscillator is going to be C1, some constant C1, plus a constant C2, times t, all of that times e to the minus omega n t. We go ahead and we substitute in our initial conditions. We will find that C1 is going to be equal to x0, and C2 will be equal to V0 plus omega n times x0. And then the solution ends up becoming that x of t is equal to the quantity x0 plus the quantity V0 plus omega n x0 times t, all of that multiplied by e to the minus omega n t. Thus, we end up finding that this is an aperiodic motion. There's no oscillations here, and it decays to 0 as time approaches infinity. We'll see a plot of what the critically damped case looks like after we go through case 3. We'll have a comparison of the two there. In fact, we'll have a comparison of all 3 cases there. All right, so case 3 focuses on the aperiodic. Actually, before I do that, for your classwork today, you're going to need to submit the completed section of case 2 as shown here. Okay, moving on to case 3. This is for overdamped. This is when zeta is greater than 0. In this case, we're going to end up with lambda 1, 2 are equal to minus zeta omega n plus or minus omega n times the square root of zeta squared minus 1. And in this case, we don't need to reverse the order or do anything to manipulate that square root because it is going to be positive as written here. And then we're going to find that our displacement will be x of t equal to a constant big C1 times e raised to the minus zeta plus the square root of zeta squared minus 1 times all that times omega n t plus a constant C2 e to the minus zeta minus the square root of zeta squared minus 1 times omega n t. That's our solution. For our initial conditions, we can find here that C1 will be equal to big fraction of x0 omega n times the quantity zeta plus square root of zeta squared minus 1 plus V0 divided by 2 omega n times the square root of zeta squared minus 1. And for C2, we're going to get something similar. We'll get first here V0 minus x0 omega n times the quantity zeta minus the square root of zeta squared minus 1 divided by 2 omega n times the square root of zeta squared minus 1. All right, so that gives us now the solution for the overdamped case. We're not going to plug C1 and C2 in there because it's just going to be a big mess. But now we're going to look at the time response for each of these, as well as what the phase plane looks like. So just looking first at this time response shown here, we've listed here several we've listed first the undamped case right here. That's where there is no damping and the amplitude never decreases in time. Beneath that, we're showing here the underdamped case. This is in this dashed black line. That's for zeta less than 1 but greater than 0. And again, omega d is always smaller than omega n, such that the period of oscillation is going to be larger for the damped case, the underdamped case, than it is for the undamped case. And you can see that just by comparing the lengths of omega d and omega n. You can see here that it starts here, and also this should be 2 pi divided by, I don't know what happened to the division there. Let's do that in red. And you can see how much longer it takes for this period of the underdamped oscillation. Now, if we look at the critically damped, shown right here, this branch, for the critically damped, it approaches 0 as fast as it can, as fast as possible. That's what makes it critically damped, because it is the smallest amount of time needed for the response to reach or approach 0. And then once we go to overdamped, it now doesn't have oscillation still, but it still takes a longer time to settle and reach an amplitude of 0. We can also look at this in what's known as the phase plane. The phase plane is a plot of the velocity versus the displacement shown here. We can now put our initial conditions as a point in the phase plane, right here. Now, for the undamped case, it's just going to, the orbit, we call these orbits in this plane, the response is just going to move around this dashed circle for all time. And we will call that the orbit. Our initial or our equilibrium point is at 0, 0 here. And so the undamped response is going to orbit this equilibrium point for all time. It's never going to change in amplitude, and thus it's just going to have this circular motion. If we look at the underdamped case, we're going to get what we call here a spiral. We're going to spiral in from the outer circle and spiral in towards that equilibrium point. So in this case, the equilibrium point is attracting the response or the behavior or the dynamics of the system. When we look at the critically damped case, it shows here that this is the shortest path possible to reach that equilibrium point. So the critically damped case gives us the shortest duration response to approach 0. And then with the overdamped response, we can see that though it's not oscillating, there's no looping around this phase plane, it takes longer to reach equilibrium than the critically damped case did. You might want to just pause the video and think about this for a little bit. In fact, pause the video, think about this for a little bit, and make sure you understand this idea of these different types of responses. Okay, so like I said, we found that the critically damped case leads to the shortest time for the motion decay to 0. And this type of motion, or at least the undamped case, this should say the undamped case, underdamped, is called, in fact, actually this applies to all of this. I'll take it back. This type of motion in general is called free vibration, and that's because the oscillator is free to move. It says here oscillate, this should say move, at its natural frequency or at its damped natural frequency. If it's oscillating, then it's definitely oscillating at that natural frequency or that damped natural frequency. Okay, with this, we're going to go take a look at example 2. We're given that a damped oscillator is released from equilibrium with a velocity of 0.05 meters per second. The oscillator has a stiffness of 250 newtons per meter, a mass of 0.5 kilograms, and a damping coefficient of 4 newton seconds per meter. We're asked to determine the peak displacement that the oscillator achieves. So I'd like to encourage you to pause the video and then take a moment to try and solve this problem. And after you work through it and see where you get, come back and watch the rest of the video to see how I solved it. Okay, so we're going to begin working on the solution. The first thing we're going to do is we're going to write out our initial conditions, and those are x of 0 equals to x0, which is equal to 0 in this case, and x dot of 0 equal to v0 equal to 0.05 meters per second. We now need to ask the question of what value or what is the case for zeta? Is it underdamped, critically damped, or overdamped? So let's say what case for zeta. We need to go and compute zeta. So zeta is equal to c over 2 times the square root of km. We'll get here if we come back up here. Let's see what our values were. So for c, we got 4. We're going to have 2 here times the square root of 250 newtons per meter times 0.5. That will then be equal to, if we go and calculate it, 0.179, and that is less than 1. Less than 1. And so we now know that we have an underdamped case. All right, in that case, the displacement x of t is going to be equal to, again, we have a 0 initial displacement, so we're going to get here that this is v0 over omega d times e to the minus zeta omega nt times the sine of omega dt. Okay, that's our displacement. We now need to find our maximum displacement. In this case, we do have a function of we have a multiplication of 2 functions of time, and so we cannot just go and determine what that is exactly. We can't just say that sine of omega dt is equal to 1 and then go and use that. Well, maybe we can. In fact, we'll see. We'll see soon. But if we do that, we're still left with what minus zeta omega nt is, and we won't be able to find what that t is because we don't have a way to determine what that is. And so, in fact, in this case, we're going to go and use the velocity, and we're going to set the velocity 0. And we know that once the velocity is 0, then we can use that time to find the maximum displacement. All right, so to find max displacement, we need to find let's just say t star for x dot of t star is equal to 0. Okay, so let's go and compute x dot of t. We will need to do a product rule here, so we're going to get first v0. In fact, we'll combine this. We're going to get big fraction minus zeta omega n v0 over omega d times the sine. We still have the exponential actually, so we'll have e to the minus zeta omega nt times the sine of omega dt plus v0 times e to the minus zeta omega nt times the cosine of omega dt, and here we eliminated the omega d in the denominator through that derivative. Okay, let us group up some similar terms, and we'll get here that x dot of t is equal to v0 e to the minus zeta omega nt times the quantity cosine of omega dt minus zeta omega n over omega d times the sine of omega dt. Okay, so we now need to think about x dot of t star is equal to v0 e to the minus zeta omega n t star times the quantity cosine omega d t star minus zeta omega n over omega d times the sine of omega d t star. And that must be equal to 0. Okay, so we again have a couple options here. Well, we really only have one option. First of all, v0 cannot be 0, because if that is, then we have no oscillations. There's no response in the system. And the e to the minus zeta omega n t star, that cannot be 0 unless t star goes to infinity. And thus, the only option is everything inside of the square brackets shown here. Everything inside there must be equal to 0. And thus, we get here that the cosine of omega d t star minus zeta omega n over omega d times the sine of omega d t star, that must all be equal to 0. From there, we can bring over the sine term, and we'll get that the cosine of omega d t star, this must be equal to zeta omega n over omega d times the sine of omega d t star. From there, we can find that the tangent of omega d t star is equal to omega d divided by zeta omega n. So now we need to find omega n and omega d. So we'll start with omega n, because omega d depends on it. This is equal to the square root of k over m, which is then equal to the square root of 250 divided by 0.5, which is equal to 22.361 radians per second. Then omega d will be equal to omega n times the square root of 1 minus zeta squared, which is equal to 22.361 times the square root of 1 minus 0.179 quantity squared, the square root of that. And if you go and compute this, you'll find that omega d is 22 radians per second. Okay, we can then go ahead and find t star. So t star is going to be equal to 1 over omega d times the inverse tangent of omega d divided by zeta omega n. This will be equal to 1 over 22 times the inverse tangent of 22 divided by 0.179 times 22.361. And if you go and you compute this, you will find that t star is equal to 0.0632 seconds. Now that we know t star, we now need to go compute what the maximum displacement is. So we're going to compute here x of t star. This is equal to v0 over omega d times e to the minus zeta omega n t star times the sine omega d t star. And then plugging in the numbers, we're going to get 0.05 divided by 22 times e to the minus 0.179 times 22.361 times 0.0632 times the sine of 22 times 0.0632. And then if you go in and compute all this, we'll find that the peak or the maximum displacement is, we'll say here, xp is equal to 0.00174 meters. Oops. And that is the solution to this example. All right, that brings us to the end of this video. In the next time in class, we will start forced oscillations and start studying what happens when you have harmonic forcing applied to a system.